Hello, my math friends. So today is lesson 3 of quadratics, and this one's a really long lesson because we have to develop a bunch of vocabulary. We have to develop some skills with our graphing calculator, and I know that for many of you, maybe you just got a graphing calculator, or maybe you got one last year, but you haven't really graphed much with it. So we're going to take some time to really try and start getting you comfortable with that, because you're going to be doing a lot of graphing in this course, okay? So what we're going to do is we're going to start with, oh yeah, I said all that to say it's super long, but in class we're going to actually do it over 2 days, okay? So you can kind of plan in that sort of way. Okay, so in grade 10, all of our graphs were linear, meaning that they were straight lines and had a constant rate of change, okay? So for every rise that I did and then over the run, that's what the slope meant. That constant rate of change means that that number is always the same. So from any point to any point, I would go up the same and over the same, up the same and over the same, or down the same and right the same, or whatever, okay? Down the same and left the same. Okay, so there were 4 different types of lines that we talked about in grade 10. I want to see if you can draw them out for me, okay? Remember that we read graphs like we read the English language. So graphs are always read from the left to the right, okay? So when I read those graphs from the left to the right, I could have a line that's going up. We say that that's a positive slope. I could have a line that's going down when I read from left to right. We say that that's a negative slope. So m is less than 0 is the way of saying that's a negative slope, right? Because m is the letter we denote for slope. And less than 0 means it's a negative number. Then I could actually have a m equals 0 slope. Do you remember what that one looks like? Yeah, it's a horizontal line, okay? And then we had a vertical line as well. Now the vertical line, do you remember what the slope of a vertical line was? Yeah, it was undefined. Good job. Okay, so those are our 4 types of slopes that we did in grade 10. Now we're going to talk about nonlinear functions. Now nonlinear functions refer to degrees larger than 1, okay? Linear functions are degree 1. If I gave you the equation y equals 3x plus 5, okay, that's a linear equation. But we call that a polynomial of degree 1. And the reason we call it a polynomial of degree 1 is because of the exponent that's sitting right here, okay? Now you don't see an exponent right there, but if there's nothing there, it's actually a 1, okay? So that's why it's degree 1. Now we're gonna turn our attention to something that might look like this. Y equals 3 squared plus 5, okay? Well, that's not a degree 1 polynomial anymore. It's a degree 2. And actually we could go to any degree. We could go degree 3, degree 4, degree 5. Totally doesn't matter. But what we're going to focus on in 20-1 for probably the first month for sure of school is really just dealing with degree 2 and what they look like and how putting numbers around the x squared changes what it looks like. Okay, so the most basic function of the most basic function is f of x equals x squared. Now, what we want to do is just get that on our graphing calculator for a second. So I want you to get out your graphing calculator. If you are a Casio kid, you'll press menu and then graph. If you are a TI kid, you'll press y equals, which is in the top left-hand corner of your graph or of your calculator pad, okay? Now, you gotta listen really carefully to a couple things if we're gonna do this together over YouTube. You want to type in y1 x squared. Now, the x has to be the variable button. There's a difference between going alpha x and actually pressing the variable button. The variable button is a button on your calculator that looks like this. It will say x, theta, t on a Casio, and then on a TI, it says that same thing, but it also says n. That's the same button, but you're looking for this button here, okay? X, theta, t button. On a Casio, it is right below the alpha button. Okay, so if you look underneath the alpha button, you'll see it. On a TI, it is to the right of the alpha button. So everybody find your alpha button and you'll be able to see the variable button very, very close by. Okay, so you want to write that and then you want to put a square on it. Okay, so Casio has the square to the right of the alpha, and TI has the square. It's 1, 2, 3 down from the alpha button. Okay. Okay, so you should be able to get a graph that looks like this once you have put that in. Now, your graph may not look exactly the same, and that's because your windows might be off. Okay, so it's probably a good idea for me to actually, why don't we share a calculator so I can talk to you very quickly about your windows, okay? Because I don't want you guys to be at home all stressed out about this. Okay, so if you take a look at my graph, I'm gonna go here and I'm gonna just change this to x squared for you. Oh, it is x squared. Okay, so just give me 1 second and I'm gonna turn this off. Okay, so now I have x squared here as well, and that's probably the picture that you're looking at right now because it's what we call a standard window. Now, a standard window goes from -9 to 9 on the x and -9 to 9 on the y. If you want to change that window, you'll notice the window I had put on the PowerPoint, it was a little closer together, so I could see it a little better. I didn't need all this wasted white space down here. So on a Casio, if you're looking at the graph, not the equation, but if you're looking at the graph, you press F3 for window. Okay, and then you could adjust that. So I'm gonna actually adjust my window. You can see here I went from -2 to 8. So I'm gonna go -2 to 8. Okay, and then on my other guy, I ended up going -4 to 4. Oh, I did that backwards. -4 to 4 on the X. Okay, and then -2 to 8 on the Y. Okay, so now when I go and look at that graph, I just press exit and draw again. Now I can see a better picture of that graph. Okay, now TIs, you do the exact same thing, but you're gonna press the window button, which is actually the kind of the F3 as well. It's the third button right at the top. Okay, you'll press window and you can do the same thing. So change your X's to be -4 to 4 and change your Y's to be -2 to 8. The scale that it says for both Casio and TI, the scale means how often they're gonna show you a tick mark. So if you change the scale to 2, you'd see a tick mark like at 0 and then at 2 and then at 4 and so on, okay? Just a quick word for Casios, because a common mistake kids do is they don't listen. Okay, so if you are here with a Casio, if you are at your equation, don't press F3 to change your window settings. Because if you press F3 right now, remember that Casio, it's all the menus are at the top, at the bottom of your screen right now. So this is F1, this is F2, this is F3, this is F4, and so on. So F3 is not window right now. It actually changes the type. It would change it from Y equals to X equals or to R equals or something like that. And you don't want to do that yet. You're not quite ready for that, okay? If you're here and you want to change the window settings, all you have to do is press Shift, and then you can do the window settings, F3. Okay, but don't just press F3 when you're not looking at this picture, okay? All right, so I'm gonna switch back to the PowerPoint now. Okay, and what do we notice? Well, the big thing I want you to notice is it's not a straight line anymore, okay? The graph is not a straight line. Remember, it is a curve. The shape of this curve is called a parabola, okay? So I have called this word a quadratic. The quadratic refers to the fact that it's a polynomial of degree 2, okay? The shape itself is called a parabola. Okay, a quadratic function is a second degree polynomial in the general form of y equals ax squared plus bx plus c. Now, I want you to look at that and I want you to say, holy smokes, that guy looks familiar because I've been factoring things that look like that for a super long time, okay? Remember I said how important factoring is. You're going to end up factoring these equations in a little while to help you get to different solutions, okay? So that's why we spent so much time in grade 10 on factoring. We were getting you ready to come into this particular type of equation, which is quadratics, okay? The graph of a quadratic is in the shape of a parabola and consists of 6 key components. So I'm going to walk you through these components now. Now, first one is a vertex, and I'm aware that my picture will be slightly above those words, but remember, you have the notes in front of you. So You should be okay if you miss a couple words there. So the vertex is the turning point on the graph. So it's where I go from going up to going down, in this case, or you can imagine that I could have drawn a parabola that looks like this as well. And if I drew the parabola that looks like this, now that would be from going down to going up, okay? Either way, the vertex is at that change of direction, okay? So the better way to say this, instead of saying going up to going down, we would say from increasing to decreasing. This would also be the highest point on the graph if you're looking at the PowerPoint one, but then if you're looking at this guy, it wouldn't be the highest point, it would actually be the lowest point on the graph, okay? And the vertex will have coordinates P, Q. Now, some of you may look at that and say, well, that's stupid. Why don't we just say the coordinates are 4, 3? Because that's what it is on the picture that I showed you. That's true. I'm just trying to get you to look at some generalities right now. So we're going to call that P, Q, okay? So the P refers to the X value of the vertex, and the Q refers to the Y value of the vertex, okay? So the vertex will have coordinates P, Q. Okay, so the next thing to talk about is the axis of symmetry. Now, what I want you to see when you look at this parabola is you can see that it's symmetrical, okay? Symmetrical means that you could draw this line in there and it would split it exactly in half. So one half you could flip over and it would be directly on top of the other half, okay? And I've drawn that line in as that dotted orange line. That dotted orange line is the axis of symmetry. So it's a vertical line that will cut the parabola in exactly half, okay? Okay, the axis of symmetry will be the vertical line that passes through the vertex. Now, all vertical lines have as their equation x equals some number. Now remember, I've called this vertex up here PQ. So if I'm looking to do the equation of the axis of symmetry, I would be looking at x equals P, okay? So this line will be the line x equals P. Okay, the domain. Now, quick little note about computer-drawn graphs versus hand-drawn graphs. Okay, you will notice that this is a computer-drawn graph, and it goes right to the edge of the kind of the window that we were showing you. Okay, anytime a graph goes right to the edge like that with a computer-drawn graph, you can assume that that goes on forever. Okay, so this is going to go all the way down and to the left forever and ever and ever, and this is going to go all the way down and to the right forever and ever and ever. Okay, because that changes your thought about what the domain and range might be. Now, if it's a hand-drawn graph, so if you are drawing a graph for me, you have to put arrowheads on it if it's a hand-drawn, but if it's a computer-drawn, you don't need arrowheads. Okay, so the domain then, if I think about going from left to right, I'm asking myself, what can X be? X can actually be anything, right? Because it's going to go to the left forever and it's going to go to the right forever. So X can be anything I want. The way to mathematically say that is X is a member of the reals, okay? Now, that works for all parabolas unless there's a context that restricts it. I don't know if you remember in our opener, we talked about throwing a snowball, okay? We talked about the fact that, yes, throwing that snowball is going to create this parabolic arch, okay? And technically, the math of that guy would go on forever, but once the snowball actually hits the ground, we're done, right? The time is useless after that. So you have to just think about the context of the problem as well, and make sure that your domain matches the context that you're talking about. But if it's just an equation, if it's just a parabola that looks like that, the domain is going to be X as a member of the reals. The range, well, you can see right away that we have a top to this, right? Y can't be something that's greater than 3 on this graph, or generally something that's greater than Q. So we have to take that into account. And you can imagine if it was this graph, there's an absolute bottom to this, right? Y can't be less than whatever Q is there. So we have two options for our range, just depending on whether they open up or down. So for a parabola that opens up, it'll be Y is greater than whatever the minimum value is, and then Y is a member of the reals. And for a parabola opening down, it'll be Y is less than whatever the maximum value is. That should say maximum there, sorry. Okay, let me just change that here for you, and I'll change it on the slide later, but that should be the maximum, less than the maximum point. Okay, All right. Okay, so now let's talk about the max and min value. As we kind of just said, the max and min value are the absolute top or the absolute bottom of the graph. Now, when we talk about max or min, we're only referring to the y value. We're not referring to the x value, okay? So it's the highest or lowest y value of the graph. For parabolas opening up, the graph will have a minimum and it will be at q. So we would actually just say, if you're asked for the max or min, you would say a minimum at q. Now, you won't say q, you'll say whatever q is, right? That's the y value of the vertex. But whatever that number is, that's what you would say there. For parabolas opening down, the graph will have a maximum at q, okay? And then we talk about intercepts. That's where the graph crosses the x or the y axis. Now, on this particular graph, you can see two x-intercepts. Oh, that's not what I wanted, sorry. You can see two x-intercepts, one here and one here, okay? The y-intercept you can't actually see on this graph, but you can imagine this is gonna go on forever and ever and ever and ever and be like somewhere over here, okay? Because that's where it would hit the y-axis. A reminder algebraically, when we are solving for the y-intercept, we plug 0 in for x and solve. When we're solving for the x-intercept, we plug 0 in for y and solve. Also, please remember that intercepts are coordinate points. So if I ask you for an intercept, you should always answer as a coordinate point. So you're not going to say I have a y-intercept at 5. You're going to say I have a y-intercept at bracket 0, 5 bracket. Okay, it has to be a coordinate point. All right. Awesome possum. Okay, so now, given the graph of f of x equals x squared, our most basic quadratic function, determine the following. So hopefully you still have that sitting in your graphing calculators like I did on the computer with you. The vertex was at 0, 0. The direction of opening, that guy opened up. Max or min value, we had a minimum value at 0. Remember, we say that it's the y value there. There's a picture just in case you didn't have one. The axis of symmetry, that's the imaginary line that goes through the center. It's a vertical line, so that would be x equals 0. Okay. Then we go to the domain. The domain would be x as a member of the reals. The range, everything greater than 0. And then the y-intercept would be 0, 0, and the x-intercept would also be 0, 0 in this one. Now, they're not usually the same thing. It just happens to be that the vertex went through the origin for this particular graph, okay? All right, you should remember all these parts for f of x equals x squared. They are incredibly important because now we must learn how to change the shape of this graph by transforming it. Now, this is where we're going to get into some heavy graphing calculator stuff, okay? As we try and play around with some things and try and learn what certain parameters around a quadratic function actually do to the function, okay? So we're going to do a little bit of an investigation here. So grab your graphing calculator if you haven't yet, graph the following functions and make a rule for what you see occurring on the graph, okay? So the first ones we're going to do are x squared, 2x squared, and 1/2 x squared, okay? X squared, 2x squared, and 1/2 x squared. So you're going to want to pause me a lot throughout this section, and you're going to want to graph because I already have the pictures done and ready to show you. So you want to pause to give yourself time to get these in, okay? I will walk you through the first one though, just to make sure you're comfy. So let me just switch my screen here. I want to share calculator. Okay, so x squared, 2x squared, and 1/2 squared. So if you're looking at your shape right now, you can just press exit. And I have x squared already there, and so do you if you were doing it with me. So you just leave that there. For 2x squared, we'll go 2x squared. Then you always want to hit enter or execute on a Casio. And then 1/2 x squared, I actually already have that typed because I was doing something else with it. But I do want to talk about fractions for a sec. So we all have different models that you're using right now for calculators. So just permit me to talk a little bit about how to enter a fraction first, okay? If you are a white Casio or an older TI, okay, a white Casio or an older TI, so you always have to put everything in linearly. So what you would do to put it in a fraction is you'd go bracket 1 divided by 2, close that bracket. That's a fraction of a half. Okay, then you would put your x squared outside the bracket, okay? If you are a newer, well, let's talk Casio since it's right in front of me right now. If you are a Casio, you like a gray Casio or a black Casio, you have a fraction button right here. It says ABC on the black or on the gray Casios, and it just actually has a picture of a box over a box. Same button right there, but it has a picture of a box over a box on the new black calculators. So you just press that and it opens up a fraction. So then you can go 1 over 2, and then you just press your right button to get out of there, and x squared like that, okay? If you are a newer TI, so a TI 84 plus, a TI 84 CE, you can do the same thing to open up that little fraction thing. You would go alpha y equals 1, okay? Alpha y equals 1. That will put the boxes there for you, and then you can put the 1 over 2 there, okay? I know that this is a little slow, but it's just I want to make sure that I have all the right conversations with you, and that I've matched things with your model. If you feel I've missed something about your particular model of a calculator, just send me an email and I can talk to you via email, okay? Don't stress. Okay, so now we're going to draw, and we're going to take a look at what actually happened to those graphs. So remember, the blue one was my original, that's the x squared. What I want you to notice is that the red seems to have gone skinnier. Now, it actually didn't go skinnier. What happens is we're actually, the y values are growing quicker because we've multiplied the y values by 2, okay? And then in the green one, it looks like it's got fatter. It looks like I've gone like this almost, right? You can imagine that if I go like this to a parabola that looks like this, it's gonna go like that. Do you know what I mean? And that's because we're multiplying the y values by a fraction now, okay? Just a quick word about window settings again. I know I've already mentioned window settings and how to adjust them. On a Casio, if you are almost what you want to see and you're not quite, like say I just wanted to go down a bit, you can actually just press your down arrow and it will adjust your window settings for you like that, okay? Or left or right, okay? Otherwise, if you have to do a kind of a bigger adjustment, then you would go into your window settings and you would adjust here, okay? If you ever want to get back to a standard window, remember I said that a standard window is -10 to 10 and -10 to 10, okay? On a Casio, when you're looking at your window settings, you will notice that F3 says standard, right? Remember, every one of these options, they tell you what you're about to do right at the bottom of your screen. So F3 says standard. I could press that and it immediately goes to -10, 10 and -10, 10, okay? Once I decide what my window settings are, I just exit and redraw, okay? On a TI, you can also quickly get back to standard window settings. You have a zoom button right beside your window button. You press zoom and then just push the number 6. That puts you back into a standard window, okay? All right, so I'm just gonna go back to the PowerPoint now. And we would look at, so I showed you the equations that I typed in. We talked about the fractions. This is the picture that you would get. Now, what are our observations? Here's our observations. When we put a number greater than 1 in for A, the graph seems to look skinnier. This is because the y values are growing quicker. When we put a fraction in, the graph looks wider, and this is because the y values are growing slower. Overall, that's called a vertical stretch. Now, the next thing I want us to try is let's play with sticking in a negative. So we actually have the exact same things there, okay? Except I put a negative in front of all of them. So if I took you back to the calculator for a sec, sorry, I know that this is a lot of switching screens, but I want to make this as helpful as possible to you. So you don't have to retype all of that. Just go back to your equation. So I just pressed exit on a calculator, on a Casio, sorry. So I can actually just right click in and stick that negative in front. Both TIs and Casio understand the difference between a negative sign, which is this guy here in brackets, and a subtraction sign. You have to be very careful. You can't start an equation with a subtraction sign. It'll give you a syntax error, whether you're a Casio or a TI, okay? Now, your graph's not registered until you hit execute, so just make sure you hit execute, and then you can go down to the next one, put the negative there, hit execute, and then go down to the next one, put the negative there and hit execute. TIs, you can do the same thing, it's just your insert is not turned on by default. So what you would do if you don't want to type the whole thing, you would just go up and TIs, just watch my mouse really closely. Right here, there's a button that says delete. And you'll notice that the second function of that button says insert. So you go second function insert and it will insert something to the left, just to save you from having to type it all over again. Okay, now what's gonna happen when I draw this? So you see I have the draw feature there. I had to press exit to get it because I was in an equation, okay? So what did happen? Everything is now opening down instead of opening up. Okay, I want you to notice that the widths are actually the same. The widths have stayed the same as they were because those numbers have stayed the same as they were. But now everything has been flipped. Okay, so I'm going to quickly go back to the PowerPoint and I'll show you that picture in the PowerPoint slide. And we're going to talk about our general observation. So when we put a number negative on A, the graph opens down instead of up. This is called a vertical reflection. Okay, let's play with Q for a second. So Q, that other one, I don't know if I said this yet, sorry. I just got so excited about showing you graphing calculators. That other one was a parameter of A, okay? We replaced x squared with ax squared. So we stuck a front, in the front we stuck an A, okay? Now we're gonna look at this and we're gonna add Q to the back. So what happens when we add or subtract a value to our function? So comparing the graphs of f of x equals x squared with f of x equals x squared plus q. So go ahead. I'm not going to show you the graphing calculator now. I think you're okay to pause me and try it yourself. F of x equals x squared is still going to remain your first guy. And then f of x equals x squared plus 4 for your second guy, and x squared minus 3 for your third guy. So you should pause me. The graph that you should have ended up is this guy, or the pictures that you should have ended up with. Now, the blue is my original. So what I want you to notice is what has the red done? It's actually gone up 4. Okay, I took the blue graph and I moved it up 4 units. You can see that my vertex is now at 0, 4 instead of 0, 0. You can see that my minimum point is now 4 instead of 0. Okay, for the x squared minus 3, I've actually gone down 3 units. You can see my vertex is now at 0, negative 3 instead of 0. And you can see that my minimum value is now at negative 3 instead of 0. Okay. All right, so the Q value seems to move the graph up if it is positive and down if it is negative. This is called a vertical translation. Okay. All right, and then the other guy we want to investigate is the P value. So I want you to take a second and put these into your equations. F of x equals x squared, f of x equals x minus 2 squared. Make sure the brackets are around x minus 2 before you put the square. And because we're changing our input here. And then the third guy is x plus 1 all squared. Okay, so go ahead and put those in your calculator. And I want you, at this stage of our little investigation, most kids are starting to feel good that they understand what's happening to the number. So then this one kind of throws you because we see that x minus 2 squared and we're like, oh, we're going to go to the left 2. And guess what? We don't. We end up going to the right 2. This is the picture that you should get. And now everybody's like, oh my dear, my brain just got blown up. Okay, no it didn't. Stay with me because you got this, man. You got this. Watch what I'm going to show you here. And this is so important. If you understand this little tiny detail, the rest is easy. It says up here, x minus whatever p is. Okay, so when I look at that, when I see x minus 2, p is 2. You see what I'm saying? And so P being a positive 2 moves me 2 to the right. Okay, when I look at this x plus 1, well, it has to say x minus P, whatever P is. So saying x plus 1 must have at one point said x subtract negative 1, which means P is negative 1, and negative 1 moves me 1 unit to the left. So if P is positive, I go to the right. And if P is negative, I go to the left. But it never looks like that in the equation because in the equation, it says x minus whatever P is. So we often are looking at that and thinking, oh, it's always the opposite of what we see. I'm not a huge fan of saying it's the opposite of what we see. I'm a much larger fan of you being able to tell me what the P value is. So always look at that and say, okay, if it says X minus P, what is the P value right now? If P is positive, I will go to the right. And if P is negative, I will go to the left, okay? So the P value seems to move the graph right if it is positive, and I just kind of showed you that again with it being X subtract whatever the P value is. I kind of showed you the P value there. And left if it is negative, okay? And this is called a horizontal translation. Okay, so now what we want to do is just go through a summary of everything we've talked about so far, okay? So let's take a look at these tables here. When we transform our original function, f of x equals x squared, that's what we're starting with, by multiplying a value of a, multiplying by a value of a to become f of x equals ax squared. So that's when we stick that a in front. That's the number in front of the x squared. What happens? Now, there were three different things we looked at. We looked at whether a ended up being a positive number, whether a ended up being a negative number, or whether a ended up being a positive number that was between 0 and 1. Okay, so a positive number greater than 1 is the first guy, a positive number between 0 and 1 is the second guy, and then a negative number is the third guy there. And again, this is the number in front of x squared. So when you're looking at an equation, you're looking for what is my a value, okay? Now, if it was a positive number greater than 1, what happened was the graph, the y values ended up growing quicker. So you can see in that red graph there, it looks like it's skinnier than the blue graph, and that's because the y values are growing at a quicker rate. So the y values will grow quicker, the graph will look skinnier. If it was a positive number between 0 and 1, so essentially a fraction, the y values, essentially I'm going to go like this, okay, which takes this parabola and it's going to flatten it out. So it's going to look wider. The y values will be growing slower. Okay, and then if it was a negative number, that flips it upside down. So I open down instead of opening up. Okay, now there are two different transformations here that we're talking about. We're talking about a vertical stretch and we're talking about a vertical reflection. If you see a number on A, that's when you talk about a vertical stretch. If you see the negative on A, that's when you talk about a vertical reflection. If you see both, like if it said y equals negative 3x squared, well, now we have a vertical stretch of 3 and a vertical reflection. You'd say both items. We never say that there's a negative stretch. Okay, we don't say I have a stretch of negative 3. I have to say that as two different statements. A vertical stretch of 3, vertical reflection. Okay, so these are called vertical stretches and reflections, and they only affect the y values. Anything vertically will only affect y, and anything horizontally should only affect x. So when I go through a vertical stretch, my x coordinates would stay the same, but my y coordinates would get multiplied by whatever the a value is. If I go through a vertical reflection, my x values stay the same, but my y values would switch signs. If I go through a vertical stretch and a reflection, again, you can still just think of that as multiplication. So my x values would stay the same, and say the a value is negative 3, I would multiply all my y values by negative 3, okay? All right, then we talked about the q value. So when we transform our original function, f of x equals x squared, by adding a value of q to become f of x equals x squared plus q. So q is always added to the end of the chain. Okay, so when you're looking for q, you're looking for the number on the end. What happens when the q value is a positive number and a negative number? Well, when the q value is a positive number, the graph is going to go up. And when the q value is a negative number, the graph is going to go down. These are called vertical translations, moving up or down. Any sort of a slide is called a translation. So, and then I'm moving up or down, so it's vertical. So again, this will only affect the y values. Okay, this will only affect the y values. Okay, then we had the p value. Now remember, when you're locating the p value, it's inside a bracket. Okay, so if you get a question let's just take a look at the board behind you for a sec. If you got a question that looks like this, x minus 3 all squared, okay? The p-value is 3 because it's x minus whatever p is. If you got a question that said y equals x plus 7 all squared, the p-value is -7. If you got a question that reads x squared plus 7, you got to be careful with this guy. There is no p-value, okay? The p-value is the one inside the brackets. There is nothing inside the brackets here. X is all by itself, so that's like an x plus 0. The p-value here is actually 0. Don't get caught into seeing this number and saying, oh, that must be the p-value. Remember, that's the q-value. We just talked about that one. That would move it up 7. We're not moving to the left or right on this guy because there is no p-value, okay? So when there's nothing there, that's like a p-value of 0. Okay, so if it's a positive p-value, I'm going to the right. And I just put in brackets here, I kind of put that +2 there so you could see it. It's always x minus whatever that p-value is, okay? And then if it's a negative number, I'm going to the left. Now, if I'm going right or left, this is now a horizontal translation. And so that one will affect the x's, but not affect the y's. Okay, awesome. Okay, and then notice that the translation goes in the opposite direction of the final form, and this is because you're subtracting the p-value. So we kind of had those conversations throughout as we've gone through this lesson together. Okay, so when you are looking at an equation in vertex form, this is called the vertex form of a quadratic. And the reason it's called a vertex form is because it shows us the vertex, right? We talked about at the beginning when I was listing the characteristics, we talked about the fact that the vertex was p comma q, right? And you can see the p, you can see the q right there. You also see an a value. So when you're looking at an equation in vertex form, you need to decide what's my a value, what's my p value, and what's my q value. Your a value is going to give you your vertical stretch. So whatever number that is, if there's nothing there, it's like a 1 there, right? And so we wouldn't say we have a stretch of 1 because multiplicatively, multiplying by 1 doesn't do anything, right? So there'd just be no stretch there, okay? So any other number though, that would be your vertical stretch. And then if you see a negative as well, you would say that as a separate statement, and that would be a vertical reflection. Okay, so when I say if a is less than 0, that means a is negative. Your p-value is your horizontal translation. If p is greater than 0, you're heading to the right. If p is less than 0, you're heading to the left. But please, please remember, it's x minus whatever p is. This negative was not included in my statement about p. So again, if you see x minus 3, the value of p is positive 3. Okay, if you see x plus 7, the value of p is negative 7. And then the q value is your horizontal translation. Sorry, your vertical translation. I'm not paying attention to what I'm saying. Your vertical translation, and then if q is positive, you're going up, and if q is negative, you're going down. Okay, so let's try that. So throughout your math career in grade 10, 11, and 12, we are going to throw at you different vocabulary. And many of our vocabulary comes from Alberta Ed's list of what we call mathematics directing words. So they are words that in a question, when you see these words, you should know kind of what you have to do in that question. And so one I'm going to talk to you about today right now is analyze. Analyze means to make a mathematical examination of parts to determine the nature, the proportion, the function, the interrelationship, and the characteristics of the whole. So it's when we do an analysis of something, we are talking about all the characteristics of that function or of that whatever it is that we can talk about, okay? So you'll notice we've guided you through the next question where we've asked you, hey, here's an equation. Can you talk to us about the vertex and about the direction of opening and about the max and about the min and about all of those things, okay? So when we do that, we're analyzing the function, okay? So the function f of x equals x squared is transformed to become the function g of x equals 2 bracket x plus 3 squared minus 4. Analyze and describe the transformations that have occurred. So I want you to go right to here and say, okay, there's my a value. My p value is -3, right? And my q value is -4. So I need to talk about each one of those items. When I do that, I have to talk about them in a particular order. Translations involve adding or subtracting, whereas stretches and reflections involve multiplying. By order of BEDMAS in math, we do multiplication before we do addition and subtraction. So we need to state the stretches and the reflections before we state the translations, okay? So we always need to go in the order SRT. That just means stretches, then reflections, then translations, okay? So starting with my stretch, I look at my a value for my stretch. So my a value is 2. So I'm going to say I have a vertical stretch by a factor of 2 about the x-axis. Okay, it's the x-axis there that's not changing. I'm going to go like this, but it's that center line there, that center horizontal line, that will remain stationary when I do that stretch. There's no reflection to talk about, so I don't need to state it. Again, there would be a reflection if there was a negative on the 2, right? I'm always looking to my a value for the stretch and for the reflection, okay? Then my p value is -3, so I have a horizontal translation, 3 units left. And then my q value is -4, so I have a vertical translation, 4 units down. Okay? All right, so now just let me clear that ink for you. We're going to talk about each one of these things. What's the vertex? Well, we said that the vertex was PQ. And we just talked about the fact that the p value was -3 and the q value was -4. So my vertex will be at -3, -4. Make sure you write that as a coordinate point. So bracket -3, -4, close bracket. Direction of opening. Well, my a value, take a look at my a value again. It's positive. When my a value is positive, I'm opening up. Okay, if my a value is negative, I'd be opening down. So I'm opening up. Now, if I open up, do I have a top to this or do I have a bottom to this? Well, I have a bottom to this, so I'll have a minimum value. And my minimum value is at Q, which is Q. Q is -4, right? You always want to go back to that equation and make sure you know where A is, where P is, and where Q is. So I have a minimum at -4. The axis of symmetry, remember that that is the vertical line that goes right through the center of the quadratic. So that has to pass through the x value of the vertex. So the x value of the vertex is at P, and that would be at -3. So we say that it's x equals -3. That's the equation of the axis of symmetry, okay? Domain, unless you're given a specific real world context, the domain of all parabolas are x, the member of the reals. The range, well, we just talked about the fact that my graph looks like this. So that means I have a bottom, and that minimum mark is at -4. So my range will be y is greater than -4. Okay. Now for the intercepts, anytime I'm algebraically solving for an intercept, I plug 0 in for the other guy. So if I'm solving for y-intercept, I need to plug 0 in for x. If I'm solving for an x-intercept, I need to plug 0 in for y. Okay. So let's start with the y-intercept. I'm going to take my equation and I'm going to plug 0 in for x. So where I saw 0, where I saw x, I just substituted in with 0. Now I've got 0 plus 3, so that's 3. 3 squared is 9, so I'm looking at 2 times 9 minus 4. 2 times 9 is 18, and 18 minus 4 is 14. A reminder though that you were asked for the intercept, so that has to be as a coordinate point. So my final answer would be 0, 14 in brackets, okay? The x-intercept might feel a little bit more difficult because we just have to have another little bit of a conversation here. But again, we're gonna plug 0 in for y. Well, where's y? G of x is y, right? G of x and y are the same thing. So I'm gonna plug 0 in for y. And now I have to solve for x. Now, when I solve for x, I essentially need to work on the things that are farthest away from x, and I kind of need to work my way into getting x isolated. So the first thing I'm going to have to do is get rid of this -4. So I'll add 4 to both sides. Okay, the next thing I'm going to do is get rid of this 2. Remember that I can't multiply that 2 in there because of the exponent, right? You have to do exponents before you do multiplication. So never ever throw a coefficient into a bracket like that when there's exponents there. So instead, we'll get rid of it. It's being multiplied by x plus 3 squared. So to get rid of it, I'll divide it. So 4 divided by 2 is 2. Now I need to take the square root. Now, when you take the square root, there's always 2 possibilities. It could be the positive possibility or the negative possibility, okay? Think about the root of 81 for a second. What times itself is 81? Well, 9 times itself is 81, that's cool. But so is negative 9. Negative 9 times negative 9 is also 81, okay? So when I ask you, hey, what's the root of 81? Your answer becomes, it's plus or minus 9, okay? This is when you're taking the square root of both sides. Okay, that's a little different than if I've given you a radical, which we'll talk about when we get into radicals, okay? Don't worry about that yet. Okay, so I'm going to square root both sides. So 2 as a square root would just be root 2, so I have plus or minus root 2, and then I've undone the square that was on the right-hand side. Okay, now to get x all by itself, I just have to subtract 3. Now instead of saying plus minus root 2 minus 3, I'm going to stick that minus 3 in front, okay? By convention, we often end with the radical. So I've just stuck the negative 3 at the front of it. So negative 3 plus or minus root 2 equals x. So that's actually 2 different points. One point is at negative 3 plus root 2, comma 0. And the other point is at negative 3 minus root 2, comma 0. Now, that should make sense if you think about this parabola. This parabola has a minimum at negative 4 and it opens up. So you can visualize there that I'd have to hit the x-axis twice, right? One for the right side of my graph and one for the left side of my graph going up. Okay, so it makes sense that we actually get 2 x-intercepts there. Okay, so that's it for this lesson. I know this one is a long lesson, lots of stuff going on. It's so important that you're doing your homework, you're checking the answers in D2L, and you're making sure you come and ask me questions, okay? That's what I'm here for. All right, have fun, and I will see you at the next lesson. Take care, guys.